are not having the advanced version. This Optisim 18 version. Already what I shared, Optisim version 7. It is enough to do this experiment. So use this do this experiment. The experiment title is analysis of LED modulation response properties using Optisim. Okay, this is a circuit layout of this experiment. Okay, already in Google, our chat box, I shared this OSD file. That is a project file, and also shared this PPT and one more file I will send later. Okay, after you are trying this experiment, after you got the output, I will tell the another interesting characteristic of this LED response. Okay, okay, just you make it note this one. What are the components we need to construct this modulation response properties for zero random bit sequence generator? Here no need to change any bit rate for first step. Okay, just you see the analysis without any bit rate. What is happen? Okay, here also NR is a pulse generator. No need to change anyone because it produces the pulses. Okay, then one LED. LED, we are going to drag and drop and set the frequency of 1300 nanometer. Okay, before you applying the frequency, you set the unit terahertz into nanometer. Okay, here also you need to you can click this button, check button. Electron lifetime is already this is a default one, 1 nanosecond. Okay, then bandwidth also you need to change 50 nanometer. Okay, then you connect after LED, you connect photo detector, pin photo detector. Okay, the next one, here also no need to change any parameter of any adjustment with photo detector, pin photo detector. Okay, then next one, low pass Bessel filter. Here also low pass Gaussian filter, low pass Bessel filter. There are so many filters are there. After getting this at the receiver section, you need to analyze this block. This is the important thing. Here, low pass Bessel filter, low pass Gaussian filter, and some other filters are there. So just you check with low pass Bessel filter. What is the oscilloscope viewer? It shows eye diagram analyzer and optical time domain visualizer, and also you see the spectrum of this LED optical spectrum with the use of optical spectrum analyzer component. Okay, then next one, the important one, eye diagram analyzer. With the we need to analyze the modulation response properties. Eye diagram analyzer is important one. Here, the input of this eye diagram analyzer is three inputs. First one is PRBS generator. That is a zero random bit sequence generator, and another input is pulse. That is a NR pulse generator, and the next one is a filter output. That is a photo detector pin output. After that, you have to get the eye diagram. Okay, just you analyze with here PRBS generator, that is a zero random bit sequence generator. Here itself we can set the bit rate. For example, we are applying 100 MB per second or 300 MB per second. Based on that, the NR reset pulse generator will be generate the pulses, and also these two sequences. That is a PRBF generator sequence and NR reset generator sequence, and also pin photo detector output that is connected with low pass Bessel filter. Here also no need to change any cutoff frequency is there. Just you connect with this eye diagram analyzer. You have to get the eye pattern like this. Afterwards, eye pattern. Okay, previously bit rate we are set 100 MB per second. What will happen? You check. Then again, you will here one concept is there. Here there are two sequences there we are given to this photo detector. Here you can see here some introduction about this demonstration of modulation response properties of LED. Okay, here these are output you need to get the eye pattern. Okay, yourself you choose the Bessel filter cutoff frequency, and also LED frequency, electron lifetime, bandwidth, and also your choice. You give the bit rate. What are the bit rate you give, then find out the modulation response of the LED. Okay. Here, and the frequency response of an LED determined by carrier dynamics, and therefore it is limited by carrier lifetime. Here, it is formula is there for carrier lifetime Tn and parasitic capacitance of LED. Okay, here this is the formula 3 dB frequency root 3 divided by 2 pi plus sum of this parasitic capacitance with carrier lifetime Tn plus TRCN. Okay, here if a small constant forward bias is applied, the influence of the parasitic capacitance of the LED can be neglected. The LED 3 dB modulation optical bandwidth is defined as the modulation frequency, and the LED power transfer function is reduced by 3 dB, so that you are giving the 3 dB at the here. Some settings are there in LED and photo detector. Just based on the function, based on the example given, you need to give the values. Okay, here for example, carrier lifetime Tn and RC constant TRC are 1 nanosecond, and therefore the 3 dB approximately 140 hertz. Okay, here the next one, the important parameter in this topic, bitrate is you said 300 MB per second, and sequence length is 180 bits. Okay, these are the inputs. Therefore, the time window is about 430 nanosecond. Time window in eye diagram. Okay, in eye diagram analyzer, the time window is about 430 nanoseconds will come. Then samples per bit are 256. Okay, so that the sample rate is 76 gigahertz. Okay, the default resolution therefore 2 megahertz. Based on the formula, you get this one. Yeah, this is a output here. Title wrongly mentioned. You don't bother about this title. Okay, here the system performance with increased bit rate. For example, previous one 300 MB per second transmission data. This one. Second eye diagram analyzer. You need to get the 60 um, amplitude, 60 meter amplitude, and the time bit is 0 to 1. Based on that, you need to get, this is your eye pattern. Uh, for that, you need to give the values. What is the values? Carrier lifetime and the RC constant TRC, which is here you need to give 1 nanosecond. Previously, the values are given 1 nanoseconds. Here, you need to change, okay, to get this eye diagram as it is. Okay, then also the frequency, you have 3 dB frequency is about 140 megahertz, and the analyze the closure of eye diagram, which is a measure for the performance of the system. The result of this one 100 MB per second, and also this one 300 MB per second. Eye diagram analyzer scope, this one. Okay, here the system performance with the increased bit rate means 100 to 300. This is 100, this is 300. Next one is a final one, improved system performance. How to improve the system performance with the 300 MB per second data, MB per second transmission. Okay, here this performance of the digital system is considerable by increasing a bit rate. Here, where you increase the bit rate here, PRBS generator, that is a pseudo random bit sequence generator. Here, based on that, and the LED 3 dB modulation optical bandwidth you can get through this eye diagram analyzer. Okay, here you can see a large improvement in the system performance at 300 MB per second compared to the latest figure having 100 MB per second. Okay, here some the influence of the modulation response of LED can be studied also by keeping the bit rate, for example, 300 MB per second, and reducing the carrier lifetime Tn and RC constant TRC. Therefore, the increasing 3 dB bandwidth. Here, previous one 1 nanosecond we given with the 100 MB per second sequence. Here, let us assume Tn TRC equal to 0.5 nanosecond. Therefore, your 3 dB will be 280 megahertz. Based on that, you calculate the frequency also. In this manner, you analyze the performance of 300 MB per second system, optical fiber communication system. Here in this manner, here you have to analyze this eye diagram. You trying to get the output diagram like this with this improved system performance. What is the previous one is you need to set the values Tn TRC as 1 nanosecond, and this is about 140 megahertz. If you choose 300 MB per second means you yourself you you need to assume TRC is a 0.5 nanosecond, and your double of the bandwidth you got. If the 3 dB frequencies will about 280 megahertz. So that the what is the summary of this one means 100 MB per second system performance, bitrate system performance having TN equal to TRC equal to 1 nanosecond, means 140 megahertz bandwidth signal you can get. Here 0.5 nanosecond means you will get 280 megahertz with the 3 MB per second bitrate system. Okay, I think I hope you are having no doubt. If you are having doubt, means you can ask.
Sir, where we have to change that bitrate, sir?
Here, pseudo random bit sequence generator. Here already bitrate equal to bitrate is there. Normally, what is the bitrate? We'll see that now. Now I'll show. Okay, this is a diagram also shared through chat box. Just to download the diagram, and just to open this example to your optimize Optisystem software. Here, this is a pseudo random bit sequence generator. Here you need to change the bitrate here. Here bitrate option is there. Just you apply the bitrate for first one 100 MB per second. Just on that you give the values. Here no need to change anything. Simulation and random numbers in this one. Okay. Then anyone having here also LED, you need to change the frequency. No need to change electron lifetime bandwidth. If I have chosen 50 nanometer. Okay, based on that you select the next one photo detector, pin photo detector. Here also no need to change anything. Here there are filter, there is a low pass. Here so many filters are there. Based on the filter you apply. For example, I already checked with the low pass Gaussian filter, is also giving better response. Here in place of Bessel filter you can use Gaussian filter. These are the options are there. Which one giving better performance, yourself you decide. Normally the best one is low pass Bessel filter, and another one is low pass Gaussian filter. Based on that you check, try to get the eye diagram as we mentioned in PPT. Based on that you need to get the eye diagram. Okay, anyone the completed means you can share your screen. Okay, then further documents you can ask. No,